We've just reviewed the work backwards strategy of problem solving, and we'll now take a few moments to review a couple of basic problems that can be solved by working backwards. Take a look at this chart. Remember that our first step when we're approaching a new data visualization, such as a graph, table, or chart, is to look at any labels that are available and to begin to interpret these. Now, we see that our heading for the chart is growth function for American girls. We see that on the x-axis, we have a label, age in years, and we have a number of different numbers ranging from 2 to 20. On the y-axis, we're not given a label, but let's say that we know that this is a growth function in height. So we're looking at the numbers 30 to approximately 70, and we can guess that we're looking, since we're looking at girls aged 2 to 20, at height in inches. This bold line here gives the 50th percentile value for the American girls. So this is the median value of height for a girl at the ages 2 to 20. We also have a number of additional lines representing different percentiles, the 5th, 10th, 25th, 75th, 90th, and 95th percentiles. So within this graph, we have information about a huge population of girls, an age range of 18 years, and a number of different values showing the whole distribution for the girls' ages at different times. Now, when we think about working backwards, we're thinking of going from greater complexity to less complexity. We have a huge amount of complexity in this chart, a huge amount of data that's represented very simply here. And working backwards, we'd be trying to solve problems that are looking for perhaps to answer a simpler question than the multitude of questions that this chart can show on its own. So as we're trying to understand what we're looking at here, we know that we have a relationship between age and height. One of the questions we'll ask is this a function? Now you'll recall that a function is a special kind of relation. It matches each value in the domain, or the x values, in this case the age, to a single value in the range, the y values, or in this case height. Take a thought about this. Are we looking at a function here? You'll recall that one of the quickest ways to check to see whether something is a function is to use the so-called vertical line test. That is, if you were to draw imaginary vertical lines across the entire range at every value in the domain, would any of these lines intersect the graph at more than one spot? I've drawn a couple of vertical lines here just to give a sense of what this would look like. And you can see that indeed the graph at each of these values of x is intersected in multiple points, each of the percentiles. So we're not looking at a function here, and this makes intuitive sense because we're looking at data about the whole population of girls in America. We're not matching each age with a single height. There's a whole range of heights, a distribution at each different age. So this is not a function. So now that we have a good sense of what we're looking at, let's see how we could use this really complex chart to solve a simpler problem. Imagine that you were asked to evaluate the median age of a 7-year-old girl. Now, one way to do this would be to collect a lot of data on your own, trying to get a representative sample of the population. Another potential approach would be to try to collect data that's already been tabulated with some Bureau of Statistics in the United States, for example, and to try to determine what the median age is for a girl aged 7 years. Or we could just look at this chart. We see that we have a median growth function. Now, the median itself is a function. Remember, there's only one point of intersection for each x value. So we walk over on the x-axis to the value of 7 years, find where we intersect the chart, and then look at what value this corresponds to on the y-axis. And we find that that's 48 inches. So the median value of a girl aged 7 years is 48 inches. So this is a great way of sort of devolving. We have a very evolved, very built-up graph, and we're finding a single data point about a single population or member of the population. Now, another question that we might ask when we're looking at a function or a relationship is whether the graph is convex or concave. Now, convexity and concavity basically relate to whether the graph is facing up or facing down. And one easy way to remember this is to think of what a cave looks like. When you think of a cave, you're thinking of an archway that points downward, something that you can walk into. And so you want to associate concavity with a cave. If the graph is pointing downward, it's concave. If it's pointing upward, it's convex. So in other words, if the graph is concave, then if you draw over some interval in the domain, then if you draw a line between any 2 points on that interval, the function will be above the line. If the function is convex over an interval, then if you draw a line between any 2 points in that interval, the function will be below the line. So let's take the interval shown here. I've drawn a line between 2 points on the function, and we can see that the median function, at least, is convex. It's all below this line. This is a convex function. Now, if we look at the next interval in years, say a few years down the line, we can see that drawing a line between 2 points gives us a function that's entirely over the line. It's pointing downward, a downward arch, like a cave, so it's a concave function. Now suppose you wanted to use this function to answer some general questions about how girls grow over the course of their lives. Again, we have a lot of data here, but one way to do this would be to calculate the average rate of change. Now if you're simply asked to answer the question of how girls grow on average over the course of 2 to 20 years, you might think of calculating the average rate of change of the girls in height over the course of those years as an adequate descriptor. Now you'll recall that the average rate of change is calculated by dividing the change in the y value over the change in the x value. So we would find the value of the median at age 2, which is a height of 34 inches, and at age 20, a height of 64 inches. We take the difference, 64 inches minus 34 inches, and divide by the difference in age, 20 minus 2, or 18 years, to give 30 inches over 18 years, or 1.7 inches a year. Now, this is a decent way of just very simply describing a complex phenomenon. It gives us the average rate of change of a median girl. However, if we take a look at this chart, we see something interesting. It seems that for the most part, growth kind of levels off at around the age of 17. So another way to describe this would be as a two-phase process. First, calculate the average rate of change over the first 17 years. Again, our values are a height beginning at 34 and ending at 64. But in this case, our top age is 17 rather than 20. So we simply calculate 64 minus 34 and divide by 15 years to give 30 inches over 15 years, or 2 inches a year. Comparing this to our first value, we have a much faster rate of change, 2 inches a year, when we look at the growth as being basically over the 2nd through the 17th years of life, than if we look at the growth as being over the 2nd through 20th years of life. And if we were to perform the same calculation in the second phase, we see that there is indeed basically no growth, approximately 64 inches to 64 inches over those last 3 years in the chart from age 17 to 20. So this process could probably best be described as a two-stage process of a 2-inch per year growth rate on average from the age of 2 to 17, and then no growth from 17 to 20. Now we see, however, that this graph isn't just a flat line. Actually, if we take a look at our average growth rate line, we can see that this line is relatively far off most of the time from the function. So we may want to describe this in greater depth, and we can always break down into even smaller phases. So if we zoom in on this area, we can see that we have a couple of different regions, one of faster increase and one of slower increase. So from the age of 8 to 12, girls grow at median 8.5 inches, and we can then calculate the average growth rate as being 8.5 inches over the course of 4 years, or 2.1 inches a year. So a little bit faster than the average over the course of 2 to 17 years. However, if we then look at the growth rate from age 12 to 14, we have a 3.5 inch difference over the course of those 2 years for 1.75 inches per year as a growth rate. So this, from the ages of 12 to 14, girls grow more slowly than they do on the average over the course of life from age 2 to 17. So we can break down life into different phases and compare to the average as well. Now, one point to note here is that we have in these two regions of the graph differences in convexity and concavity. In fact, this first time period from 8 to 12 years that has the faster growth rate is convex. Convexity is associated with an increase in growth rate, or an increase in rate of a function. And in the second period, when we have the slowdown in growth, we see that the function is concave. It's all above the line, shaped like a downward arch or a cave, so it's a concave function. Concavity is associated with a decrease in the rate of change of a function. So we can also associate convexity and concavity transitions with changes in the growth rate of the function. So we're seeing how we can look at something very complex and break it down to make some simple conclusions by using the